All right, everybody. Wow, I love this mic. It's fantastic. We'll do the karaoke afterwards, though, Gaurav, okay? You and me. Excellent. Well, thank you all for being here today, for attending today. My pleasure to introduce our speaker. It's Gaurav Kamat. We're here to hear about his PhD work. He'll be defending his thesis, so naturally we'll have a public portion. Definitely welcome questions and answers from audience, and then we'll excuse everybody, have a private portion afterwards. So let me just say a few quick words. It's hard to because there's a lot to say about Gaurav. It's been amazing working together with him. He had an outstanding undergraduate career at UC Berkeley, academically, scholastically, research-wise. Joined our group as a first-year PhD student, joining a team of over 30 people, and instantaneously became one of the most experienced and proficient users of TEM as he walked into the lab and really started contributing in so many ways involving that and many other things over the years. Just outstanding scholarship. We'll see a lot about the fundamentals. He's really had a keen eye towards diving into very hard, very difficult, very complex interfacial phenomena. You'll be hearing a lot about that work today. What you might not be so aware is how much also he's been contributing to our community more broadly. He has spent 3 years on the leadership of GSAC versus vice president originally, and then 2 years as GSAC president. He's had contributions on so many fronts there, including in diversity, equity, and inclusion within our group and in the broader chemical engineering community. One thing that very few of you might ever get to know is how crucial Gaurav's leadership was about 3 or so years ago, when there was just a lot happening in the DEI space in our department, and still today. But really, there was just 3-4 years ago, it was a very challenging time where we were addressing a lot of key issues, and his leadership, working together with the faculty and the staff and representing the student body, led to a lot of very good outcomes. And I really thank Gaurav a lot for his leadership on that. That is something that is not very visible to the broader community, but something I wanted to share with you all today. He'll be talking about a lot of fundamental science, but make no mistake, he has a keen eye towards changing the globe for the better and having an impact at scale. In fact, in this latter stages of his PhD, co-founded a company on that front, is already getting funding for that opportunity, which is where he'll be transitioning to next. And so we're really excited to see how that pathway goes. And you wrap up all of this as somebody who's just got really the academic excellence, the scholarship, the leadership, the contributions to community. He was awarded also our department's most prestigious award for graduate students, which is the Mason Fellowship. And so with that, I just want to thank Gaurav for all the contributions to our team and to broader chemical engineering and beyond community. And please join me in welcoming him to the stage today. Thank you so much, Gaurav.
Thank you so much for the very warm introduction. Warm welcome to all of you here in the room and also those joining us virtually from around the world. So unfortunately, a thesis title isn't necessarily the best title for a public talk. It's a lot of very specific words in there. So I'll just kind of get started with the motivation and kind of patch things together as we go. I'll begin with one of the takeaways from this year's Breakthrough Energy Summit, which is that energy is prosperity. And the meaning behind this is that as the per capita energy consumption of part of society increases, so does its economic output and the level of prosperity. Wealthier regions consume more energy and enjoy a higher standard of living as a result. And this is something that you can see all over the world. And unfortunately, there's also a large disparity across the world because of this system. So to zoom in on one specific area, electricity generation by source, which is something a lot of people think about, right? Coal, natural gas, a lot of fossil fuels make up electricity generation around the world, but it's not just electricity. If you think about the materials and the physical substances that we use to construct buildings, to do all kinds of things, textiles, the total final consumption by source, you see coal, oil, natural gas are way, way higher in addition to the electricity. About 96% of all materials on Earth have some fossil fuel component. So fossil fuel derived energy and materials really do enable the modern way of life. Now, usually this wouldn't be a problem, except that our human activity has been affecting the entire planet. Carbon dioxide concentrations historically going back 800,000 years, which we have pretty good ice core data for, you can see only until about 1911 they were below this line. and then they started shooting up as we extracted fossil fuels from the ground. Now, 1911 is pretty recent, but nothing here is new. If you look at ambient lead concentrations in the world, you can actually see that they spiked around 2,000 years ago when the Roman Empire was at its height and a lot of metal smelters were running at peak capacity. So if we want to stop environmental impact, you'll need, an effort on the scale of empires. You'll need an entire humanity-wide effort to kind of address this problem. So what are some solutions, or what can we do about this problem? Well, electrocatalysts are one specific solution that I'll be going over today. So electrocatalysts kind of fit in here between a lot of these feedstock chemicals and a lot of the chemicals, materials, fuels, and energy that we use in a modern energy system. And electrocatalysts let us kind of interconvert between renewable energy to produce fuels and materials and replace our dependence on fossil fuels. So how does an electrocatalyst function, and how does it actually accelerate reactions of interest? Well, here's an example of a hydrogen evolution reaction. So green hydrogen production is based on this reaction. If you start from protons and you make hydrogen as your goal, it turns out that doing that reaction sort of in a vacuum is very, very energetically intensive. A catalyst will enable this to go faster by creating an intermediate state, usually on a surface. And once it's on that surface, depending on the binding energy of that metal for the certain adsorbate of that reaction, you can enable a much, much faster reaction. Now, here's another example of a reaction, the oxygen reduction reaction, which is used in metal air batteries and hydrogen fuel cell cathodes. The example here is to say that we can actually predict how good a catalyst may be depending on the binding energy of certain key intermediates on that surface. And so you can see metals like platinum, palladium, and silver form some of the best oxygen reduction materials. And this is kind of the state of the art in terms of how catalyst activity is predicted. But of course, these are all just material constraints. Catalyst effectiveness also changes with the environment. An example of this is in biology, where you have all kinds of molecular catalysts inside your body, enzymes, that are within cells, and they all need these different pockets that have different local pHs in order to function properly. Now, electrocatalysts are no different, except that this reaction happens at an interface, right, where the surface of the catalyst meets this liquid phase. Now, the liquid phase can be extremely complicated. You can see that these red and white specks here are water molecules. You also have ions and a large gradient in electron density, as well as an electric field. And all of this is happening in a region called the microenvironment. And it's really this region that I want to look into in order to understand it better and kind of make better technologies based on it. So detailed surface studies is the goal of today's presentation. So electrocatalysts enable surface reactions in steps. So taking that oxygen reduction reaction from before, you start with molecular oxygen and it will stick to your surface. Depending on how it sticks, it may want to stay as O2, or that oxygen-oxygen bond may break. And you have this whole kind of cascading set of steps that all have different energies. And you can end at either hydrogen peroxide as a product, or you can end at water as a product. Now, the microenvironment that I mentioned before can affect each of these steps in the mechanism differently. These are all happening at different kind of relative energies and all happening at different rates. So as an example of that, you could have, ionic adsorbates, for example, interfering with the adsorbate and just competing for the same active site. You could have them, inducing changes to the local electric field so that it's harder or easier to perform one set of that reaction. They can interact with the dipole moment of certain adsorbates and therefore change their energy of adsorption, more directly chemically interact and change things like the transition state. And you also have effects such as pH buffering. Of course, any ion that's in your double layer or in your near catalyst region is going to be surrounded by water molecules just based on its hydration, and that can change the local pH in very unexpected ways. And lastly, there's some evidence that charges actually take very layered appearances in terms of stacking water and ion in order to balance the charge that's emanating from the surface. So given all of this background, how do we actually measure an electrocatalyst performance? So this here is a rotating disc electrode setup. It's one of the most common electrochemical setups for measuring performance. Your electrode is immersed in liquid and it's spun around. You have a counter electrode that kind of balances the reaction, and a reference electrode that provides you a stable potential so that you know actually what potential things are happening at. And this shape here is a cyclic voltammogram, which is taken by adjusting the potential and recording the current density that your catalyst is able to achieve. And for the oxygen reduction reaction specifically, as this sort of moves further to the right, closer to 1.23 volts, which is the versus RHE, I should say, that's sort of the onset or the equilibrium potential. So as it moves further to the right, you have a better catalyst that onsets earlier. So an example of an effect in terms of the microenvironment is shown here to the right, a pretty old paper from 2007, perchloric acid and potassium hydroxide on a silver electrode. So you can see, for example, the clear shift in the onset potential based on just what environment you put the same material in, but also a very large change to selectivity. In KOH, you have almost no hydrogen peroxide that's produced, but in perchloric acid, you actually do have quite a bit of hydrogen peroxide. In some cases, it's almost 100% selective. So another thing I mentioned before, and it showed up in that picture, was ionic spectators. And they're called spectators because they don't participate in the reaction just like oxygen does, which reacts away to form water or hydrogen peroxide. So lithium, sodium, potassium, rubidium, and cesium are just spectator ions that are not undergoing any changes, but you can see that they do have an effect that's based on actually the hydration dynamics of those ions. And that's because near the surface, you have these charged ions that have hydration shells. So you have ion adsorption, which is how these ions sort of stick to the surface. You have solvation, and you also have charge screening, which is how charge emanates from these ions and from the electrode, and how those things interact in the double layer microenvironment. And all of these sort of affect what's going on near the surface. So in the past, there have been some studies of this region, particularly with anions, and a lot of them just sort of indicated the negative effects of certain ions being present. So on a platinum surface, if you have 0.5 molar perchloric acid, and you add very, very tiny amounts of chloride ions, we're talking even 10 to the minus 4 molarity compared to 0.5 molarity, you actually see this onset potential shift left. So your catalyst is getting worse because of competitive adsorption. But a lot of studies just kind of left it off there and commented that certain anions are not really good for catalysis. But there's another way that I kind of look at this, which is, can we understand and engineer the interface to actually enhance performance? So the way that people have typically thought about take a given catalyst, to make it better, you can either increase the number of active sites on that catalyst, or you can increase the intrinsic activity of each active site on that catalyst. And what I'm saying is, what if there's another kind of direction to take in terms of electrolyte engineering? Can we do something in the electrolyte phase that kind of, in addition to all of these efforts, can provide a parallel kind of way towards better performance? And to go through how I sort of see this playing out in the grand scheme of things, right now we're at these foundational studies of the interface of microenvironments, and these inform a lot of catalyst development and reaction condition optimization in small-scale test devices. And after sufficient testing, they can be deployed into new technologies for energy and sustainability. Here I'm just picturing a hydrogen fuel cell that's been commercialized. And the great thing is, once we have these new technologies, we can kind of restart this loop and understand how those technologies behave in the real world and how we can make them even better. So if we understand electrolyte effects better, we can develop better performance, more degradation resistant, and more selective catalysts. So throughout my PhD, I've kind of explored both sides of this, which is to say the electrolyte phase and the catalyst phase. And these are sort of just the different chapters of the thesis I've written. But I'm really just going to be focusing on the left side here today. So just the electrolyte-based studies. I'll just briefly mention, in terms of the catalyst phase, I got to look at how adding a very small layer of manganese on silver affects the oxygen reduction reaction, and actually used X-ray techniques to understand how oxidation state changes affect catalysis. I also looked at these manganese antimony oxide nanoparticles and doping various metals within them to understand how their activity and stability are modulated with online stability techniques. And lastly, a project where I looked at changing the ligand. That is, the oxygen in this case, if we swap that out for a nitrogen or a sulfur, how that affects everything. So those are all catalyst phase things, but I'm going to stick to electrolyte phase today. So the first question here that I had is looking at these electrolyte effects and just using a rotating disc electrode. How does an ideal polycrystalline platinum electrode, how is it actually affected by anion identity in electrolytes of an identical pH? So here's what some of this data looks like. These are all on the same kind of platinum substrate, and they're just biased to different potentials and in some cases different gaseous saturations to understand different components of the catalysis. So here you can see perchloric acid, nitric acid, and sulfuric acid for the ORR. You see that as you change from perchloric to nitric and sulfuric, you start getting worse and worse in catalysis. And on the right here, you have the exact opposite of oxygen reduction, which is oxygen evolution. And there you also see a similar thing, that this perchloric acid is actually the best. The trend is flipped when you're looking at the opposite reaction. And then nitric and sulfuric are a little bit worse. And that's what these bars are essentially showing here. So we see distinct differences in both ORR and OER performance with anion identity. But the interesting thing is if we do the same experiment just at a lower potential where you have hydrogen now present, now we're looking at the hydrogen evolution reaction, the one I showed at the very beginning, and also its opposite reaction, which is hydrogen oxidation. We don't really see that much of a difference in magnitude compared to what we saw before. So for hydrogen reactions, you have anion-based differences that are a little bit less pronounced. So kind of looking at these oxygen-based reactions versus these hydrogen-based reactions, one tool we use to understand why this may be happening is physics-based modeling, specifically with density functional theory. So some collaborators of ours were able to essentially model the delta G of adsorption of these different anions on a platinum surface. And what this delta G of adsorption means is as you go lower on this axis, you have a stronger interaction with your surface. As you go higher, you have a weaker interaction with your surface. And one thing you see is right here where the ORR and OER potential range is, you have a strong anion effect because you see that these are interacting a lot more strongly. They're much lower in their delta G adsorption compared to a weak anion effect when you're over here in the HER and HOR range. And so this strength of anion interactions varies at different potentials, and it's an example of competitive adsorption on a platinum electrode that's changing your electrocatalysis in different ways. Another thing we saw in this study, particularly for the oxygen evolution reaction, is as we cycle this platinum electrode up and down in potential, you actually start seeing the performance degrade a little bit over time. And if we look at why that may be, this is a potential versus pH diagram that shows what phases are kind of expected to be thermodynamically stable at various conditions. So as you go from this platinum solid phase and you apply a higher and higher potential, you see that platinum oxides are actually starting to form on the surface. And if we look at how exactly, right, as these cycles go down, how exactly that rate of oxidation or that rate of catalyst deactivation changes with anions, the apparent deactivation varies by anion. So what ion you have present appears to also change how fast your platinum may oxidize and therefore deactivate your active platinum surface. So as a quick summary of this chapter, we saw that platinum experiences changes based to the oxygen-based reaction specifically based on anion present. We saw that density functional theory can indicate evidence for competitive adsorption in conjunction with the experimental data we collected, and also that anion species can induce different rates of platinum oxidations under oxygen evolution potentials. So moving to, having a clicker issue. There we go. So moving to the next chapter, I wanted to look at interfacial dissolution. So no catalyst will stay active or stable forever. every catalyst will degrade in some way. The question is how and how fast. And so I looked specifically at how these different anions actually impact dissolution on the surface of metals during oxygen reduction for a number of key interesting oxygen reduction metals that kind of are some of the most studied in terms of being the most active. So how do anions and electrolytes of identical pH impact dissolution for single metal ORR catalysts? So I'll go into a little bit of the kinetics and thermodynamics of corrosion chemistry. I already introduced this plot before, which is potential versus pH, but this one shows a little bit more schematically. You can have a material that's immune, which is sort of completely stable in its metallic form. You can also have passivation, which means it forms an oxide layer on top of it. And you can have corrosion, which means it's actively corroding or dissolving away. Now, you can have anodic corrosion, which is the most typically studied. As you go to higher and higher potentials, materials become less stable. But there's also some evidence for cathodic corrosion, that if you bias your potential very negative, you can actually induce corrosion ionically at a very low potential. And this is kind of the scheme to have in mind when we're talking about corrosion. So a metal, atom will become a metal anion, a metal cation, but it can't just do this by itself. It needs to kind of put those electrons somewhere, and it has to have a driving force to do that. And typically what happens in a lot of systems is you have surface reactions that can kind of accept some of those electrons. So as this ion can oxidize, it'll feed electrons in to a surface reaction. Now, if we connect this system to an external circuit, we can also push or pull electrons based on what potential we apply to the surface. So we can encourage or discourage this dissolution process based on how we sort of apply the potential. And an Evans diagram is sort of what tells us how exactly this happens. So if I look at the intersection of these two lines here, first, this line here describes copper oxidation. So copper going to copper ions and 2 electrons. Well, those electrons have to go somewhere. And in this case, if oxygen reduction is available on that surface, if oxygen is available, then it will feed into there. And you'll actually form a mixed potential that's in between both of these sort of equilibrium potentials, but the net current through your electrode is 0, because we're just talking about these local electron flows. As you apply potentials then, you can actually have non-zero net current. So currents either flowing, positive or negative kind of through your catalyst that you can measure. So corrosion in a potential governed condition is actually a very complicated phenomenon, both thermodynamically and kinetically. And so that's something I wanted to understand. So kind of developing a framework to talk about this, current density is one of the things I'd mentioned. So we kind of make an axis for that. And then dissolution is the other one. So if we then categorize what exactly is happening at each of these parts of this quadrant, you essentially get little pictures like this. So I had showed on the previous slide this sort of cathodic plus dissolution. So you have a current that's flowing kind of net this way, but you're also supporting it with current that's due to the oxidation and dissolution of metal ions. But you can also have chemical dissolution where everything is, there's no net current flowing through your electrode. So these are just some of the possibilities that are available. And I tested this on these specific metals, which turn out to be very interesting for oxygen reduction. And what degradation means in catalysis is not necessarily a well-defined term. You have things like electrochemical degradation, which means as you sort of cycle this thousands and thousands of times, you start to move your cyclic voltammogram left and have a lower activity. And that's purely an electrochemical measurement. But as we mentioned before, you can also have material degradation, where you can have ions coming off of your surface, you can have phase changes, oxidation state changes. And an ideal system would be able to kind of combine elements of both of these so that we could actually understand what's going on. Now, unfortunately, when I joined the lab, we didn't actually have a system such as this. So we built one. We bought some equipment, specifically an inductively coupled plasma mass spectrometer, and we built a system that lets you measure all the different corrosion products, specifically the metals, and designed a cell with thanks to Jaime to actually put realistic current densities through this device so we could understand what's going on. So special thanks to Michaela and Melissa for helping set up the system. It's very cool because we got to have some important people come through the lab and show them this is one of the world's few systems that's able to do this kind of measurement of simultaneous electrochemistry and dissolution. And essentially how this works is you take your electrolyte, but instead of putting it in a single reactor, you're just going to pump it through an electrochemical flow cell that has conditions tuned so that it can actually produce realistic current densities. And all the liquid that comes out of there can feed straight into an ICP-MS. It's not that simple. There's a lot of things here at the interface that need to be figured out. But in essence, you have your potentiostat, which is changing your potential and recording the current density, just like all the measurements we've seen. But now your ICP-MS can actually measure any number of dissolving elements as a function of that same time. And if you combine those two data sets, you can have a cyclic voltammogram, but you can also have a mass cyclic voltammogram that says, as a function of potential, where exactly is my dissolution happening? So this is really important because it's online quantification of dissolved species during reaction conditions, during relevant conditions. So here's what some of this data looks like. This is a palladium foil, and this was done for 5 different acids, all pH 1. And what you can see is that perchloric, sulfuric, and nitric, all of these cyclic voltammograms are higher in onset. But then you have hydrobromic and hydrochloric that don't really quite do much oxygen reduction in these settings. Now, on top of that is stacked the dissolution rate. And the units of this dissolution rate are how many nanograms per centimeter squared per second. 10 to the minus 9 grams. This is a very, very tiny dissolution rate. And in the case of hydrochloric and hydrobromic, if we read this over, it's on the order of hundreds of nanograms per centimeter squared per second. And in the case of nitric, sulfuric, and perchloric, we do have differences, but you see they're all less than 1. So you have huge order of magnitude differences in how this electrolyte effect changes dissolution on a single metal. And the mechanism for why this happens or how this happens is actually very similar to platinum. And this is taken from a paper that studied platinum. So as you increase your potential, you're going to have oxygen adsorbates on your surface that will sort of roughen the surface over time. And that leads you a little bit of this, initial dissolution on the upward potential sweep. And then as you sweep back down, that roughened surface is going to dissolve a little bit faster compared to your smooth surface. And so on your way down, you're going to have this large bump in dissolution that happens. So, and another thing we can do with this setup is kind of compare the different metals in terms of their dissolution in a single acid. So these are all taken in perchloric acid, and we can see that one, they have vastly different onsets based on where this cyclic voltammogram is sort of taking place. And you can also see that as this onset kind of tends to get worse, you also tend to have a little bit higher rate of dissolution of your catalyst, which is a little counterintuitive based on what a lot of catalyst activity and stability trends tend to look like. Now, another thing we can study with this is gas saturation. I mentioned we had an electrolyte reservoir, and you can choose to put either oxygen or nitrogen in that system. So in oxygen-saturated electrolyte, this is copper foil in a variety of different electrolytes. You can see what's going on here in terms of the activity. If I switch this and I now sparge it with nitrogen, one, you see all of this oxygen reduction current density has sort of flattened out and it's gone closer to 0 current. And the only current that's sort of happening here is based on either hydrogen evolution or other competing reactions. And you can also see that there's little changes, very subtle changes to the dissolution profiles and also the order of, the magnitude of the dissolution. And so this is important to know because the gas saturation or the operational conditions also change your dissolution. I mentioned competing reactions very briefly. Those can also influence your stability. And here's an example of that. This is on nickel foil, oxygen saturated. I have nitric acid and I have sulfuric acid. So without any additional information, if I looked at this, I would say, well, nitric acid has a much higher onset for the ORR because there's oxygen present. And it does have a little bit higher, maybe similar or higher dissolution in some areas, but it's at a much higher potential. So that looks really good. The issue is we have to also do this under nitrogen to make sure that we're actually confirming oxygen reduction is happening. So if I do this under nitrogen, well, you actually still see the same current density trend here, but that current density has now flattened out for sulfuric acid. And that's because you actually have a competing reaction. You have nitrate reduction that is happening on your nickel surface when nitric acid is present. And what that means is these reduction reactions, such as nitrate reduction, can be a sink for electrons. So if there's some electrolyte species that is willing to accept electrons at a certain potential, it will speed up the rate of dissolution of a catalyst. So it's always important to understand how your different spectator or non-spectator species change your electrocatalyst stability. And the last thing I'll mention is that these mass cyclic voltammograms are sort of like dissolution fingerprints. They tell us a little bit about the mechanism of dissolution. So I mentioned that palladium and a few of the other metals have this sort of oxide-mediated dissolution pattern. But if we look at manganese, right, manganese has much more linear-looking shapes. And given that this is just a log axis, it means as you increase your potential, your degradation or dissolution rate is going up exponentially. So the hysteresis in your dissolution, which is the difference between the forward and the reverse sweep, can be related to some material phase change dynamics. So to quickly summarize, online ICP-MS can identify regions of good activity and stability for brand new materials that no one has really ever tested before. You have ORR, but also other competing cathodic reactions in the presence of anions that can affect a metal's surface stability. And you have mass cyclic voltammograms, which are these shapes here that contain some information about surface level material dynamics. So a very powerful, platform in order to study new types of electrocatalysts and all their interactions. So going into the last stretch here of the double layer structure, this is specifically referring to during reaction conditions, how exactly are cations, anions, other types of species, what are they kind of doing at the surface? It's a very, very difficult region to measure. And it, of course, varies a lot based on the electrolyte that you choose. So how does electrolyte composition affect electrocatalyst surface restructuring and charge distribution in the interfacial region? That was the main set of questions that I wanted to understand. And the pictures for that look something like this. So surface restructuring, right? You have your surface reaction that's going on the surface. You can have, oxides that may form on your surface. You can also have metal atoms that jump around and roughen the surface. All of this depends on, what anions or other species are present. And you have anion distribution, which is referring to how exactly are anions solvated or unsolvated? What are they doing near the surface? And specifically, the potential that you apply to the electrode has to decay into the electrolyte in the bulk. Now, how exactly that happens in this very close interfacial region is a very complex phenomenon. And if we could have a technique that can understand something like this and extract this potential profile, that would be very, very helpful. So we actually combined X-ray and then previously some of the mass spectrometry techniques on this ORR model system to understand how exactly these different surface level phenomena are playing out. Now, one important framework to keep in mind is how, one property of these anions that we found to be specifically important is how chaotropic or cosmotropic they are. Now, it's a very strange sense of a word, but it almost, it means what it sounds like. Chaotropic sounds like chaos, and that's because it, puts a lot of chaos into the system in terms of water's hydration structure. So chaotropic anions, such as these nitrates and perchlorates that we saw a lot of, these are weakly hydrated and they disrupt water-water interactions. And that's because they're singly charged, they're rather large anions, and they have very weak hydration shells. They don't have a lot of water molecules that need to interact with them. Compare that to something like phosphate or sulfate, which are doubly or triply charged. You now have much stronger hydration, and these actually promote water-water interaction. And it turns out that this is quite important for the hydration energy and the hydrogen bond formation, because that is something that happens near your surface that affects your catalyst environment interactions. So in order to study this, we used a technique called grazing incidence X-ray diffraction at the Stanford synchrotron radiation light source. Essentially, it's one of the world's brightest sources of light. And it's all kind of X-rays at a specific energy that you choose, and you can put them into your system in various ways to understand different dynamic phenomena. So this cell that I've shown here has a working and a counter electrode that are opposite each other, and it has little windows that you can shoot the X-rays through in order to measure specifically the surface if you align everything just right. So this is what the cell looks like when it's put in. You have this beam that's coming in, you have a cell right there, and you have a two-dimensional XRD detector that's placed just behind it, and then all of the supporting equipment, which is a gas saturator, you have a pump, you have your gas line and a potentiostat. So just like the experiments we do here in the Stanford lab, we can take this entire setup and move it to the Stanford synchrotron and repeat it in a flow cell in order to look at what's happening on the surface. And this 2D detector is really interesting because it can also provide additional surface measurements for texture. So we can look at what may be happening on the surface. Now, in terms of what this data looks like on the 2D detector, it generates an image, and that image looks something like this when you take it raw. You'll see that there's some of these like very well-defined rings, but there's also this big diffuse ring. And that diffuse ring is actually just due to solvent scattering. So you have water and anions in your system that's kind of scattering your X-rays. So you need to collect a background, and that kind of just shows you your diffuse ring. And when you subtract those, now you get a really nice picture of the diffraction rings of your material specifically. If we do a little geometric transformation, so instead of rings, we can turn these into lines. Now 2 theta versus chi is what you're looking at here. 2 theta is sort of like your main diffraction angle, and chi is sort of like a specular versus off specular, which means is the outgoing X-ray sort of in line or not in line with the incoming X-ray. So if you take a horizontal line across this data and you just read it out, it looks a lot more like a traditional X-ray diffractogram that tells you about crystal structure. And if you take a vertical line, it can tell you a little bit about how the surface texture is and some information about the orientation of different facets of your material. And when we do an intensity calibration in this background measurement, because we just leave the cell in the same place and run an electrochemical protocol, we can actually enable a quantitative study where we can see differences in diffraction intensities and draw conclusions from the data. One important thing is what angle you choose. I mentioned it's a grazing incidence technique, which means that you're putting these X-rays in at a very, very small angle in order to get just the surface region's signal. So if I choose an angle of, say, 5 degrees, I definitely get my signal from the sample, but I also get some other peaks that are coming from substrate layers and other things that are underneath. Not desirable because it's not as surface sensitive as we want. But also, if we go to 0.1 degrees, your beam footprint is no longer as large. You're just not going to get enough signal from that. So 0.2 was sort of like the sweet spot that we chose for our measurements. And that turns out to a penetration depth of just a few nanometers. So we're measuring the crystallinity in just the topmost few nanometers of our sample. And this is what some of that data looks like. Now, unfortunately, on palladium, when we did this measurement from 0 to 1.1 volts, we didn't really see a lot of changes in the crystalline structure. But when we did this on silver, we saw quite a few changes. So one, you see that these peaks are sort of getting higher in their intensity. Again, everything has been calibrated in reference to the incoming intensity. And so this means that your system is getting more and more crystalline sort of as you apply higher potentials. And then past certain potentials, you may even be forming a transient kind of silver oxide. Again, this is in the topmost few nanometers, so it's not a bulk silver oxide, it's just at the very top region. And it could be oxygen adsorbates, for example, causing this signal, because silver is one of those materials that's strong binding. It really likes to have oxygen stuck to the surface compared to some other ORR materials. So palladium didn't change, but silver had an altered surface crystallinity and phase structure, as we saw. Going on to nitric acid in silver. So previously it was perchloric and now nitric. We see a lot smaller magnitude of changes, although we didn't test it in as wide of a potential. And perhaps the most interesting one is this one, which is in sulfuric acid. So as you apply higher and higher potentials, you can actually see these peaks start to skew to one side. And that's evidence of local surface strain. So as the silver atoms kind of nearest your surface either start to stretch or contract depending on what's going on the surface, it seems like your anion actually has some effect and some role in causing changes to your silver surface. So certain electrolytes appear to induce surface strain as a function of these applied potentials. Now, that was everything we did. I didn't mention the other study on kind of the orientation of the different crystallites, but that was the main takeaways that we found in terms of just the crystallinity. Moving on to the other thing I mentioned, which was the anion distributions. So we use X-ray reflectivity, again, at the Stanford synchrotron light source. And this is a very familiar setup because you actually use the same exact cell. You just perform a slightly different alignment. And now your detector, instead of being a two-dimensional detector, is sort of on this long arm that's much further out so that you can measure very slight changes to your signal. And X-ray reflectivity data is a little bit weird. It looks something like this because this is what your setup is looking like. Your incident X-ray beam is reflecting off of your sample. And if there's multiple layers in your sample, they're going to interfere with each other on the way out. The light waves are. And so if you have a perfectly smooth surface, you're going to have this very, very, very bumpy signal because of the constructive and destructive interactions. But if you have even slight levels of roughness anywhere on your surface, you'll see those bumps, but then they'll start to damp out. So you can use this to kind of see the roughening that's happening on your surface. And because it's the same exact cell and sample morphology that we did for the X-ray diffraction study, we can bridge a lot of the same conclusions that we see. So here's an example of some of this data for palladium in nitric acid. As we start at open circuit potential and then kind of apply lower and lower potentials as time goes on, we don't really see any major changes in the reflectivity signal. And if we compare this to a cosmotrope such as chloride or hydrochloric acid, and we specifically look at this region, you can actually see that there's these fringes that you're seeing are starting to disappear as you go lower and lower in potential, whereas that's not really happening in the case of nitric acid. And what that means is that there's surface roughness changes. Specifically, hydrochloric acid has a much larger role in roughening your surface compared to nitric acid. So if I take all of that data and kind of back calculate what exact roughening is happening, this is what that data looks like. So nitric and perchloric don't really change the surface roughness. If anything, they get a little bit lower in surface roughness, whereas these other three induce a lot more changes. And it's interesting because this trends almost exactly with this setup that we had before, where you have chaotropes that actually do very well in terms of not encouraging surface roughness. And then you have others like bromide or bisulfite that do a lot more. Now, I'll mention roughness isn't necessarily a bad thing. If you roughen your surface, you can open up a little bit more electrochemically active surface area that your material can take advantage of. So if you found conditions in which you can roughen your surface without dissolving it, that may actually be beneficial to the catalysis that you want to do. And then the last thing you can do with X-ray reflectivity is actually extract electron density profiles, because these X-rays are actually reflecting off layers of electron density. because your sample is very layered, and so is your double layer that's just above your surface. So you can use the reflectivity signal to back out how that electron density looks near your surface. So if we take a data set like this, which was for sulfuric acid, it looks something like this. Compared to open circuit potential, all of these other potentials have very slight differences to electron density. And one interesting thing I'll note is that 0.4 volts here seems to be the one that's kind of tightest or closest to the electrode, because this is distance away from the electrode surface. And it's interesting because that's close to a point known as the potential of zero charge, when you have no kind of overall charge that's built up at your surface. So it's very interesting that when we measure it, it's kind of tightest to there, because it's very hard to confirm a lot of these measurements without doing additional theory calculations. So we saw here that cosmotropes have a lot of perturbations in electron density. This same data for perchlorate and for nitrate didn't really show large differences in charge or electron density. But in case of all the cosmotropes, you did see differences. And here's an example of one of those other differences. This is in hydrobromic acid, where you also see pretty large differences in the electron density. Now, I'll mention that these are relatively weak compared to cation interactions. This is a literature example of a platinum electrode where they had cesium present, and you actually get these very strong peaks only a few angstroms away from your surface. And that is corresponding to layers of charge that are forming on top of your surface. Now, it doesn't seem like anions are doing anything nearly that strong. And part of that is because while you're doing a cathodic reaction, you may have an excess of negative charge that can push anions away. However, it's still interesting to note that we can resolve some of these differences. And based on all the previous work, they actually have a lot of implications on catalysis. So HBr has very strong interactions, but cation interactions tend to be stronger. So to quickly wrap this up, this flow cell architecture that we used with thin film catalysts, it can give you a lot of surface-specific information, not just in the two setups that we use, but in a variety of different setups. We saw that chaotropes can impact surface crystallinity and oxide phase formation on silver during the ORR, and that cosmotropic anions may promote roughening processes and change the double layer structure on palladium, whereas those chaotropes really did not. So to wrap it up, this is kind of, again, an overview of everything I talked about. I focused on the electrolyte phase, but there is also an entire catalyst phase discussion that will be saved for another time. Before I completely wrap up, I'll just mention a few future directions for any aspiring people in the room that want to continue some of these studies. Bubble formation is one of them that is actually quite interesting, specifically for reactions that evolve gases. Now, hydrogen evolution is one of those, and I didn't study that one specifically. I did oxygen reduction, which doesn't evolve gas bubbles. But there's a lot of evidence that shows that using an electrolyte such as sulfuric acid changes the forces on a bubble that is on your electrode and changes at what size it wants to detach from your surface, just based on a simple force balance. Now, this is important because you want to free up as much of your surface as possible. So you want bubbles to take up less and less of your surface in order to get the most out of your catalyst. And electrolytes may be one way to get there. There's also pulsed potential electrocatalysis. So a lot of projects recently have been looking at not just applying a single potential, but kind of going back and forth between two potentials to see how you can change, the double layer structure and take advantage of different species. And lastly, water and the surface interactions. I focused on anions specifically, but water also adsorbs to your surface. And there's other techniques such as the X-ray crystal truncation rod scattering shown here that actually let you resolve, well, in perchloric acid at 0.5 volts, I'm 2.47 angstroms away from the surface. And at 0.9 volts, I'm 2.14 angstroms away from the surface. It's that sensitive in terms of how you look at the water interactions. So to close out, if we understand electrolyte effects better, we can develop higher activity, more degradation resistant, and more selective catalytic interfaces that can show up in a lot of modern technologies to help us decarbonize and reduce our impact on the environment, yet maintain the prosperous way of life that we all enjoy. So with that, I'll conclude the scientific portion of everything here. I want to give a huge thank you to my committee that's all sitting here in the front. You all have been a great source of support and mentorship, and I just learn so much from you every time I get to have a meeting with you. I'll also thank the Jaramillo Research Group and some of our funding sources. So the Toyota Research Institute, as well as the US Department of Energy, funded the vast majority of the science that I was doing. Also had support from the NSF GRFP and the Mason Fellowship, as Tom had mentioned earlier. Some of my scientific collaborators from the Toyota Research Institute, from the Stanford synchrotron radiation light source. A lot of those experiments in that third chapter were not that easy to set up. So I'm very grateful for their advice in terms of how we could do all of these measurements. The Stanford Nano Shared Facilities for facility access and instruments. SunCat Center Theory for doing some of the supporting calculations to help make sense of the measurements we get. A big thank you to the Burke-Stevens group. I was an affiliate of that group and spent a lot of time there. Specifically from Michelle, I got a lot of personal mentorship, and I'm very, very thankful for that. And the Leidendecker group in Germany, where I got to spend a summer doing research. Very thankful for all the scientific input that everyone gave me there. I'll thank staff, facilities, and external supporters from our department. As Tom mentioned at the beginning, I spent a lot of time in the Graduate Student Action Committee, and I got to work with a lot of these very wonderful people in our department quite often. Very excited to have worked with them. The SunCat Center administrative staff, the Arriaga Science Center at SLAC, Thermo Fisher for helping us set up the ICP-MS, Circularity Fuels, which is the company that Tom mentioned at the beginning that I'm very glad we have everyone here from today, and some outside mentors, primarily from my undergraduate time. And friends, a lot of you in the back here, thank you for your support all along the way. A lot of photos to share here. And I think one of the biggest takeaways or big life changes that I had from graduate school is when one of these friends specifically becomes family. So she's here in the front row and also serving as the moderator for this session. So thank you, Netra, for all of the amazing support you've given me. And as you gear up towards your own thesis defense, I hope I can be just as supportive. And lastly, to family. I have an amazing family that's always supported me every step of the way. And I'm very thankful for all the support, all the late nights, all the traditional and untraditional lessons I've gotten from everyone along the way. So with that, I'll wrap up. Thank you so much for your attention, and I'm happy to take some questions while we have time.